Okay, guys, look up here 1 second. Here's what's happening. Here's your unit circles. We are about to unwrap your unit circles so that we can graph this on an XY plane. Now, here's your important parts, or your quadrants. Your 0, your 90 degrees, your 180, your 270, your 360. What it does is this. If I took a string and I mapped this out, and I marked off these angles, and I lay them out like this. There's my 0, there's my 90, there's my 180, my 270, my 360. If I look at all your y values, aren't those your sine values? So when I start at the 0, I am a sine of 0. When I go to a 90, I am a sine of 1. When I go to a 180, I am a sine of 0. When I come to the 270, I am a sine of -1 and back up here to the 0. Do you see it sketch out your curve? Now, it probably went fast. The t-step is the guy that regulates how fast or how slow it goes. But if the t-step is off, then you actually don't get a really good curve. But we can try changing your t-step. I can change your t-step and make it a little bit slower. Let's see if this makes it a little bit slower. Now when you graph, you can kind of see, there's your 180, there's your 180, there's your 270, there's your 270, there's your 360. Did you see it? If it goes a little bit slower, now we can probably make it go a little bit slower. See, it's not as sharp as it was with the 0.1, but it will just go a little bit slower. And let me see if I can make it a little bit slower. I think this might not work, but we'll try. Here's your 0. And it's very, very slow. Look, there's your 45, and your 45s cross each other. There's your 90 coming up. There's your 1. It's moving along here. But do you see it? Graph piece for piece. It's coming up to 180, and 180 says I should be back at the 0. There's your 180. Now you're coming down in your lower quadrant, where sine and cosine are both negative. Isn't the side dropping below the axis where it's negative? Sine is also negative. Up there's the 270 at the -1. Now isn't sine also negative in quadrant 4? Isn't it negative below the line in here? Do you see it corresponds? And then it comes back up to the 0. So it's kind of a cool way to see this. Another way that's nice on this, let me just set my step back to normal. I kind of like it when it goes a little slower, because this kind of went a little bit too fast. But what we can do is, we can jump from one graph to the next. Now, just watch for a second. Hit your trace button. Do you see where it's sitting at the 0 on the circle? Well, if I arrow up, I jump to my graph one. And the 0 is sitting at the 0 of the graph. Okay? I'm going to arrow back to my circle. I'm going to move my circle up to the 90 degrees. Now remember, the problem with traces, you don't always get exact. 90 degrees is pi over 2. 3.14 divided by 2 looks like about 1.5, 1.7 something or other, right? 1.5 something, 1.57, whatever. There's your 1.6. And look, isn't your y real close to the 1? But you can't get exact on a trace. And you can't do a value on this. But do I see it? Now watch me jump over to my curve. See where the 90 came out on your curve? Now jump back, arrow back to your circle, and go down to 180. So pi is approximately 3.14, right? So when t is at 3, my curve, my y value, is getting closer to the 0. I don't know if I'm going to get closer than that. Let me see. Yeah, there's a 3.1. 3.2, 3.1. Now when you arrow back over, there's your 180. See it? So you can kind of see it unraveling your curve. I just thought this was kind of a little cute exercise so that you can see it coming off your circle and onto your curve. Because what we're going to do is take all your angles off of that circle and graft them onto this curve. Okay? Now, we're going to graph, and I graph my graphs off of your unit circle. You know me, I love patterns. Rather than pick up your calculator and put it in your calculator, I found more kids had trouble going from degrees, setting up where should my scale be. Do I do it every 90? Do I do it every 45? You're still going to have to figure that out anyway. So how we're going to sketch this is exactly what your sketch did just now. At your 0, these are all your y values. So build me a little thing like this. At your 0 degrees, at your 90 degrees, at your 180, at your 270, at your 360. So you're going to say, at your 0, our y's are our sign. 0, 1, 0, -1, 0. That's going to be your cycle for your sine curve. We're looking for our max. That's a 360. Our max, our mins, and our zeros. That's what's going to help us sketch your curve. All the guys in the middle, like the 45, here's a 45-degree angle. You know your sines and your cosines are the same. They're 1 over radical 2, which remember when you put it in your calculator was 0.7. Sure, they'll fall right between our 0.7s. We'll be able to see them. But we don't care about graphing the little parts in between. We just want to hit your max, your mins, where's across the x-axis, your zeros. So if we follow this pattern, 0, 1, 0, -1, 0, this will graph your sine curve. This will graph your sine curve. Sorry about that. And remember, even though we graph your sine curve from -2 pi to +2 pi, this thing is continuous. It does not have a beginning or an end. It's like your sine waves. These are your sine waves. It's like your radio waves. You ever learn in music when they do your frequencies? Like what happens when something gets louder, what happens when something gets a higher pitch, what happens to your music waves. So your waves are like this, going through, right? If you change your frequency, what happens to your waves? Like the pitch, they change. They get like this. I want louder. I want to make it louder. Don't my waves go like this, right? If you change your amplitudes, if you change your frequency, then it goes faster, slower. Excuse me. So our waves change just like that. Now, the opposite side just continues your curve down. It just continues the pattern in the negative direction. Okay, now, they should be nice smooth curves. My curves, sorry, are never nice and smooth because I'm writing sideways. My excuse. So, for a sine curve, what is your domain? What angles can we use? Oh, and whatever angle I pick has a sign, doesn't it? Doesn't matter how big, how small. It's like your unit circle that keeps traveling around and around and around in either direction. What's your range in your sine curve? -1 to 1. Okay? And don't forget, we use those values, so they get hard brackets. Now, your basic format for your equation is this. Basic. Without adding any transformations up and down or without any phase shifts in here. Your basic. Where A is your amplitude. Now, what your amplitude does is this. Your amplitude measures from the resting position the distance to the top of the curve or the distance to the bottom, the crest of the curve. Like if you see a wave come, the wave starts at sea level, the wave goes up and comes down, like the crest. So an amplitude is a distance. An amplitude always has to be positive. An amplitude cannot be negative because it's a distance. Does that mean I can't do this? This tells me, just like in our transformations, I have a stretch of 2, but my negative gives me a reflection. My amplitude is not negative 2. My amplitude is always positive because it's a distance. But remember when we did these before? The negative gives you a reflection. So we'll talk about those. Now, if I change my amplitude, an easy way to do this is to take your pattern and multiply everything by your amplitude. Times it by a half. 0, 1/2, 0, negative 1/2, 0. So my new curve, 0, 1/2, 0, negative 1/2, 0. I keep the same curve, but the amplitude changed. That's all I'm changing, amplitude. And it changes the same on the negative side. Now, B is the tougher one. B is the frequency. I want you to write this down. Frequency, let me just get my mess out here so I have space, is how many complete cycles means I've gone around my curve 360 degrees in 2 pi, or in 360 degrees. How many complete cycles did I make in 360 degrees? Now, for my red sine curve here or my black sine curve, how many complete cycles did I make? 1 complete. I went all around my unit circle, all the way around back to 360. I made 1 complete circle. That's the 1 right there. The 1 in front of the X is how many cycles did I make? How many complete cycles? Now your period takes off from your frequency. It says 2 pi over B. If it's easier to relate in degrees, then relate it in degrees. So 2 pi over B is 2 pi. It says, how long to complete 1 full cycle? And in this case, didn't it take me 2 pi to complete 1 full cycle? Right? It kind of silly when we use the 1 and the 1, but we're going to change that in a second. Okay? Now, if you rather work those in degrees, do them in degrees until we get there. Here's the most important part. How many quadrants did we go through to make a complete circle? 4. We always go through 4 quadrants. So no matter how many times we change this frequency, we still have to complete 4 cycles. All right? So with that thought, let's jump down to this guy right here. I gave you the transformations for the trig because I think they look even worse than the logical stuff. So we'll talk transformations over the next couple days. But most of the time, you really don't recognize them as a transformation as much as you do a frequency or an amplitude change. We'll adjust them. So the difference between this and your parent curve is what? What's changing? Your basic sine curve was a 1. So your frequency is now 2. And so that tells me I have 2 complete cycles in 2 pi. Watch. I'm going to use degrees for a minute. I have 2 complete cycles in 360. I need to go like this. 1, 2, before I hit 360. Now, my period says, how long does it take to complete 1 cycle? So if I do 2 in 360, how long does it take for me to complete 1 cycle? 180. 360 divided by 2, right? Here's your 360 divided by 2. It's going to take me 180 degrees. Here's the formula. 2 pi divided by 2. Doesn't it take me pi radians or 180 degrees? Now, watch how we're going to graph this. Our sine cycle was all going around your unit circle was 0, 1, 0, negative 1, 0. And if you can't remember it, you take it right off of these values. Your sine is your y. So 0, 1, 0, negative 1, 0. We're going to have to do this twice. So here's the easiest way to do this. You just told me it's going to take you 180 to complete one cycle. So come to 180. Put a mark. How many quadrants does it take to go around my unit circle? 4. So section this into 4 equal quadrants. Here's half, then section half of each. And then we've got to do it one more time. So from pi to 2 pi, section it 4 again. Now, we're just going to go through this with our max, our mins, and our zeros. 0, 1, 0, negative 1, 0. There's 1. We're going to do it again. 0, 1, 0, negative 1, 0. Do I have 2 complete cycles in 2 pi? Right? So all you need to do is figure out how long is it going to take you for one cycle, then section that one cycle into 4 quadrants. It takes me 4 quadrants to get around the unit circle. And here's why you have to know that anyway, just to put it in your calculator. Because when you do the scale part, or set your table, if you set it every 90 is going to give me this one, this one, this one, this one, this one. All my 90s are going to say 0. How am I going to graph off of that? You would have to change your scale to say, give me every 90 divided by 2, every 45. I need to know every 45. I need 4 quadrants in 180. 180 divided by 4 is 45. So you're going to have to think that anyway. So it's so much easier without your calculator. We're sketching. We don't care about all these little guys in between. We know they'll fall in between there. Now, let me adjust this. I'm going to just change this a little bit and do, and I know I didn't give you a space to do it, but you can put it somewhere. Y equals the sine of 3x. Just make a little grid. Just make a little grid and map off 90, 180, 270, 360, like that. Make a grid, a real fast grid. So, because my frequency is now 3, it says I need 3 complete curves, let's work degrees, in 360. How long is it going to take me to complete one curve in degrees? How many equal sections? I need 3 of them in 360. I need 360 degrees. I need to put 3 of these things in 360. So divide 360 divided by 3. 120. It's going to take me 120 degrees to complete one. I got to go like this. 120, 240, 360. I need 3 of them. How many quadrants does it take me to go around the circle? 4. So 120 divided by 4 gives me what? 30. Every 30 degrees, I need a quadrant. Stay with me. 30, 90. How many 30s come in 90? 3. So between each one of these, give me 2 equal tick marks. Okay. Start like that. Now, let's map out how long it's going to take for one cycle. 120. So look, 30, 60, 90, 120. Every 4, so I need 4 quadrants. 1, 2, 3, 4. 1, 2, 3, 4. See it? Now do your pattern for each one of these. 0, 1, 0, negative 1, 0. That's 1. I need 2 more. 0, 1. I did. I'm off. Because you know what it is? I can't stand in front of this. 0, 1, 0, negative 1, 0. Okay, and do it again. 0, 1, 0, negative 1, 0. Do I get 3 frequencies? Yep. Now, whether you use your calculator or not, that 30 degrees is key to this. I need to be able to break it down into how long each one will be and break that down by 4s. So how big is each quadrant? So not so bad, right? Question? Okay, let's go the opposite way. Oh, by the way, is this a horizontal stretch or a shrink? Shrink. It's like an accordion. This one works a little bit differently. You've got a shrink in here. You just shrunk the period size. This one works a little bit differently. We shrunk it down. So we've got a little bit of a vertical shrink. And we'll attach these to your transformations tomorrow. This one tells me my frequency is now 1/2. That means I have half of a curve in 360 degrees. Without any formulas, I want you to think about it. If it takes me half of a curve in 360, how long is it going to take me to make a complete curve? 720. How many quadrants do I need to go through? Well, how many quadrants in a circle to make a complete curve? 4. Now I need 720 degrees just to make one curve. I got a half and another half. So it's going to take me 4 quadrants. How big is each quadrant going to be? 180 degrees. So I got to go half of my curve right here. So I got the 0, the 1, the 0. Half of my curve in 360. I'd have to do another 360 to get to 720 to do the other half of my curve. My frequency is 1/2. 2 pi over 1/2 says keep, change, flip. Says 4 pi. 4 pi is twice 2 pi, right? So 2 pi and another 2 pi. A 360 and another 360. It's probably easier in degrees for you to find out where your quadrants are. If we did this and we said 360 and we did 4 pi, if we divide 4 pi by 4, yeah, every pi, that one wasn't so bad. When you get to like pi over 3, pi over 6, that's a little bit tougher. So we're looking at your frequency, and we're adjusting how many curves in 360. Now your amplitude, that can go along with anything that we do. If we put a 2 here, we just multiply everything by 2. Instead of being at the 1, it's at the 2. And the zeros will stay the zeros. It just will go like this.
Will it always be working on this, on that chart, or is it going to be different?
What do you mean?
On the graph up there, or are we going to have to draw our own eventually?
This is how you're going to do it.
Because right there, if it's 2 pi, you only need half of one.
You only need a half.
So you wouldn't even have to do any of that.
No, but I wanted you to see that how it works and how to still find your quadrants, because it's going to take 720 degrees to complete it. So we still divide by 4, but in your head you said half, which is nice, it's half. The cosine curve looks a little worse, because the cosine curve starts here and goes like this. So half of your cosine curve is going down here. Everybody can get the sine, but struggles with the cosine because the cosine still comes across. But if you get the concept of a half, that's great. But it does match up when we do the rest of the way when we think it out. So I kind of wanted you to just think it out. So any way that you do this, you will still come out the right way. I want you to be a little bit